Greetings and salutations to everyone. My name is Daniel Bauman Nyamwaya, and I'm a happy individual today. I'm here to present to you some of the research work we're doing over the course of the semester for my course of Artificial Intelligence in Healthcare. I am a graduate student pursuing a master's in data science here at Michigan Technological University, and I'm here today to talk to you about AI-driven pneumonia prediction, the centric approach using machine learning. Let's dive right into the problem statement. Pneumonia, as you all know, remains as one of the leading causes of illness and death worldwide, especially in vulnerable locations and populations. Early detection remains key when it comes to improving outcomes. In this research project, I particularly explore how artificial intelligence, specifically machine learning, can help predict pneumonia using structured clinical data, things like age, symptoms, lab test results, and vital signs. My goal, or rather our goal, was to develop a model that accurately identify pneumonia risk, supporting clinicians in early diagnosis, even in the absence of imaging. Our approach was quite simple: dimensionality reduction coupled with predictive modeling. The dataset that we were using, that I used as applied in this particular research study, had over 70 features. To be quite honest, had around 83 features, full of a lot of information. So you can clearly see there was high dimensionality. And you know, the thing that comes with high dimensionality is what is called the curse of dimensionality, where instead of the model generalizing properly, or fits. So to address this situation, we applied principal component analysis, where we tried to reduce the data into smaller components while retaining as much variance, be quite clear, as much as 95% of the variance in the data. We then fit this data, this reduced data, the components, to several models, baseline models such as logistic regression, all the way to more advanced models such as the random forest and XGBoost, just to see how they perform that on this particular clinical data. Some of the code highlights that you can see in front of you, you can see the process of how the data looked like before and after applying principal component analysis to the data set. Of course, prior to this, all the standard pre-processing techniques were applied, and even SMOT was applied to oversample the minority class and generate synthetic samples of the minority class. So there, afterwards, DCA was applied, and you can see the data was reduced to around 5 principal components that encompass around 95% of the variance of the data. Training was applied, models were trained, and this was the evaluation metrics that were obtained from the various models that were trained on the clinical data, logistic regression, random forest, and XGBoost. And from the comparison, you can clearly see that XGBoost came out on top. In terms of a holistic evaluation, came out proper. In terms of the principal components, you can clearly see these are the top 5 features per principal components that contributed the most to how the models were deriving their predictions. You can clearly see that things such as age contributed most to principal component number 5, and then other features such as pneumo, pathogen, and admission PSI, which you will see the descriptions in the next slide deck. So here are the 5 principal components, and this comes into the component of explainability, because we fit the model, we evaluate the model, but when you know in this particular health domain, you have to come up with explainability of how you think, or rather explain how the models were bringing about their predictions. When it comes to principal components, you can clearly see these are the features that contributed the most, and their various interpretation of why they contributed the most to the predictions that the models were making. So therefore, in conclusion, our models performed well overall. demonstrating that machine learning can apply clinical settings when it comes to pneumonia detection. I should mention, though, that the models are performing quite well on data that was biased towards the majority class. This was even after applying techniques such as oversampling, undersampling, and finally SMOT to create synthetic examples of the minority class. So clearly, the project, the main challenge for this project was that it faced a lot of data issues when it comes to getting the actual data. It was quite hard and difficult. So in terms of the future direction, the future direction for this project is quite bright. First, try and combine structured clinical data with image-based data for overall and holistic predictive modeling when it comes to pneumonia. Sorry. As we know, most of the research right now is into using image data and transfer learning. But I'd like to explore opportunities where you can combine both and have a holistic view of how to predict pneumonia. Applying techniques such as transfer learning is important to curb the issue, the lack of data, where we look for a model that has been trained on a large data set, a clinical data set, and find ways of tuning that particular model so that it works with the current data set that we have. Federated learning will also come into play because we want to introduce diversity into the model prediction. Expose the model to diverse data, and then it performs well overall on a holistic level. And eventually, this project should be deployed, or rather, we're looking to deploy it into a full-fledged tool that can be applied in the clinical setting, where we envision where someone or like a medical practitioner is able to input the symptoms of the patient, rather the clinical symptoms of the patient, and also the image data from the patient, and then get a holistic prediction of whether the person has pneumonia or not, and even subtypes of pneumonia. So that's the future direction of where this project is taking us. So thank you for listening to me. Leave a comment in the description. In the description, you'll also, in the comment section. In the description, you'll also find a link to the GitHub, and you'll get access to the notebook that was used in this particular project. You get also a link to the dataset and all the various documentations that are involved in this particular project. Thank you, and be well.